Welcome to lecture number 13 on measure and integration. If you recall, in the previous lecture we had been looking at the Lebesgue measure, Lebesgue measurable sets and its properties. We will continue that study of Lebesgue measurable sets and its properties today itself. We will be especially looking at the translation invariance property of the Lebesgue measure and then Lebesgue measurable sets vis-a-vis topologically nice subsets of the real line. So, let us recall that we have defined what is called the Lebesgue measurable sets, and that gave us the space, the real line, the Lebesgue measurable sets and the Lebesgue measure. So, this was called the Lebesgue measure space. And the Borel sigma algebra of real line, the Borel subsets of the real line form a sub sigma algebra of Lebesgue measurable sets. So, these properties we had seen, and now today what we are going to look at is the following. Recall on the real line there is a binary operation of addition, you can add real numbers. So, this operation can be used to transform subsets of the real line. So, let us take a set E contained in real line and define what is called E plus x. So, E plus x is defined as all elements y plus x such that y belongs to E. So, it is the set E which is translated by an element x. So, the question is E belonging to L. If E is Lebesgue measurable, does this imply that E plus x is Lebesgue measurable? And similarly, we will also look at the second question, namely if E belongs to B R, if E is a Borel subset of real line, does it imply E plus x belongs to B R? So, these are the two questions we will start analyzing. So, the importance of these two questions is the class of Lebesgue measurable sets, is it invariant under translations, and is the Lebesgue is the class of Borel subsets invariant under the group operation of translation on the real line. So, these two questions we will answer in the first to start with. So, to answer the first question, let us recall that Lebesgue measure is nothing but the restriction of the outer Lebesgue measure. So, and the Lebesgue outer measure for real line is defined as the infimum of sigma lambda of intervals I, where these intervals form a covering of E is a subset of union i's I equal to 1 to infinity, and i's are all intervals. And keep in mind the remark, we said you can choose these intervals i's, ij's to be open if necessary. So, whether you take all possible coverings of E by intervals or all possible coverings of E by open intervals, both will give you the same value, namely the Lebesgue measure of the Lebesgue outer measure of the set E. So, let us start. So, let us start with a set E which is Lebesgue measurable to show that E plus x is also Lebesgue measurable. So, this is a question. So, to show that, recall what is definition of a measurable set. So, to show that for every subset y of real line, we should have Lebesgue outer measure of y is equal to Lebesgue outer measure of y intersection E plus x plus Lebesgue outer measure of y intersection E complement plus x, E plus x complement, sorry. So, that is what we have to show. Now, let us start observing that we are given that E is Lebesgue measurable. So, E Lebesgue measurable implies for every subset y of real line, the Lebesgue measure of y is equal to outer Lebesgue measure of y intersection E plus outer Lebesgue measure of y intersection E complement. Now, our aim is to transform this E to E plus x. That means, we should be looking at the properties of the outer Lebesgue measure of a set in terms of translation. So, let us observe. So, let us note that if a set E is covered by a union of intervals I j 1 to infinity, that is, if and only if E plus x is covered by union of the translated intervals, that is I j plus x, j equal to 1 to infinity. That means, every covering of the set E gives a corresponding covering of the set E plus x by the intervals I j plus x. Note that if I j is an interval, I j plus x also is an interval. So, if E is covered by intervals I j, we get a corresponding covering of E plus x by the intervals I j plus x, and conversely, given a covering of E plus x, we can construct back a covering of E by looking at by translating by minus x. So, this property obviously implies that Lebesgue measure of a set E is same as the Lebesgue measure of the set E plus x. So, this observation implies that the Lebesgue measure of a set remains invariant under translations. So, this is a property. So, this is a important property of the Lebesgue outer measure we are going to use to conclude that if E is Lebesgue measurable, then E plus x also is Lebesgue measurable. So, as we said, E Lebesgue measurable implies for every subset y, we have got lambda star of y is equal to lambda star of y intersection E plus lambda star of y intersection E complement. And now, observing that Lebesgue measure is invariant, outer Lebesgue measure is invariant under translations, we can write this as lambda star of y intersection E plus x plus lambda star of y intersection E complement plus x. Okay. So, here we are using the fact that lambda star is translation invariance. And now, a simple observation will tell you that y intersection E plus x is same as y intersection it is same as y intersection y plus x intersection E plus x. So, meaning that if you take intersection and translate, that is same as translating and intersections. So, that is simple set theoretic property. So, the first term here is equal to lambda star of y plus x intersection E plus x, and similarly the second one will give you it is lambda star of y plus x intersection E complement plus x. So, that is using the fact that lambda star is translation invariant and intersection translation is same as translation intersection, they commute with each other. And now, this property is true for every subset of y. So, I can replace y by y minus x. So, implies replace y by y minus x, we get this is also equal to. So, lambda okay. This property is true for every. So, let us replace. So, lambda star of y minus x is equal to lambda star of. So, y plus x minus x. So, that is y intersection E plus x plus lambda star of y plus x minus x. So, that is y intersection E complement plus x. So, in the above equation we have replaced y by the set y by y minus x. Okay. So, this is true, and now observe lambda star of y minus x is same as lambda star of y. By translating y or by x or minus x does not affect. So, we get for every subset y lambda star of y is equal to lambda star of y intersection E plus x plus lambda star of y intersection E complement plus x. Now, a simple observation tells you that this set E complement plus x is same as E plus x complement. So, first take the complement and then translate, that is same as saying first translate and then take complement. So, it is purely a simple set theoretic exercise which you should be able to verify easily. So, we get lambda star of y is equal to lambda star of the first y intersection E plus x plus lambda star of y intersection E plus x complement, and hence this implies that E plus x is Lebesgue measurable. So, we have proved the first property, namely if you take a Lebesgue measurable set E and translate, then the translated set also is Lebesgue measurable. So, another way of saying the same thing is that the Lebesgue measurable sets are translation invariant. They remain, the class of Lebesgue measurable sets is translation invariant. And we have already seen that Lebesgue outer measure is translation invariant. So, that means that the length function is translation invariant on the class of all Lebesgue measurable sets. So, this proves the first property. So, we have answered the question that if E is Lebesgue measurable, then E plus x is also measurable. Let us look at the next question, that if E is a Borel set, can we say that E plus x also is a Borel set? So, to answer this question, we need some topological properties of the real line. So, let us look at the topological properties what we are going to look at. So, the question is, if E is a Borel subset of real line, does that imply E plus x is also a Borel subset of real line? So, for that let us observe, consider the map. So, consider the map from real line to real line, where y goes to y plus x for every y belonging to y. So, x is fixed. So, this is translation. So, this is the translation map from real line to real line, and the observation is that this map translation is a homeomorphism. So, what does homeomorphism means? That is, it is 1 1 on 2 and both ways continuous. That means, this is continuous and the inverse map, because it is 1 1 on 2, that also is continuous. So, this is an important property, very basic, but yet important property that we are going to use to prove that if E is Lebesgue measure, if E is a Borel set, then E plus x is a Borel set. So, let us look at, so consider, so to prove our requirement, let us consider the collection say S. So, S is a collection of all subsets which are Borel and which have that required property, namely E plus x belongs to B R. So, look at all Borel subsets of real line, which such that the translated set is also a Borel set. So, we are going to prove two things about this. One, that the class of all open sets are subsets of S, and second thing we will prove that S is a sigma algebra. So, once these two properties are proved, all open sets are inside S and S is a sigma algebra. So, these two properties will imply that the sigma algebra generated by the class of all open sets is inside S, and that is nothing but the Borel sigma algebra. So, the Borel sigma algebra will come inside S, and that will prove the required property. So, we have to only prove these two facts, namely that if you take an open set, then it belongs to S. That means, if I take an open set and translate, that should be a Borel set. But that is again obvious by the fact that translation is a homeomorphism. So, if E contained in R is open is an open set, then the set E plus x is also an open set. So, that is also an open set. In fact, that is a very simple property to prove, because if you take if E is open, that at every point there is a open interval inside E, and the translated one will be inside E plus x. So, that is easy to verify, or one can simply verify by saying that E plus x is an open map, or the translation is a homeomorphism. So, this is an open set. So, this implies the first property, that all open sets are subsets of S. And the second thing, that it is a sigma algebra. So, for that note, empty set, the whole space are both open. So, they belong to S. And second, if a set E belongs to S, that implies E plus x belongs to S, is a Borel set, but that implies this is a sigma algebra. So, E plus x complement is also a Borel set, right, because it is a sigma algebra. So, must be closed under complements. And now, a simple observation, that this set E plus x is nothing but E plus x complement is same as E complement plus x. So, this is same as this. So, that belongs to B R, and that implies that E complement belongs to S. That is same as saying E complement. So, the class S of subsets of Borel subsets of real lines, either it translates or Borel sets, includes empty set, the whole space, it is closed under complements, and let us prove that this is also closed under countable unions. So, third property, namely, so let E n be a sequence of sets in S, implies that E n plus x is a Borel set in R, and Borel sets being a sigma algebra, that implies union of E n plus x also belongs to B R, and hence now here is a simple observation, that this set is same as you first take the union and then take the translation. It is same as first translating and then taking the unions. So, that belongs to B R. So, basically translation commutes with all set theoretic operations, that is the observation we have been using again and again. So, this belongs to B R. So, that implies union n equal to 1 to infinity E n is a set in S. So, we have proved. So, hence open sets are inside S, a sigma algebra. So, implies that the Borel sigma algebra generated by open sets, which is the Borel sigma algebra, is inside the smallest sigma algebra generated by open sets, namely the Borel sigma algebra, must also come inside S, and that is a subset of B R. So, hence all are equal. So, this proves the second fact, namely, if E is a Borel set, then its translation is also a Borel set. And once again it emphasizes the use of the technique that we had called as the sigma algebra technique, namely, we wanted to prove that for every Borel set E, the translation is a Borel set. So, note, so we collected all the sets which have this property, and we proved two facts, namely, the open sets are inside this collection S, and S is a sigma algebra. So, that implied that the smallest sigma algebra generated by open sets, which is nothing but the Borel sigma algebra, also comes inside S. So, this technique we will be using, we have been using and will be using quite often, is called the sigma algebra technique. So, you want to prove some property about subsets of a set X, collect them together and try to show that those sets form that collection forms a sigma algebra and includes the generators of the required sigma algebra. So, we have proved that under translation the measurable sets, the collection of Borel sets are very well behaved, and we get a translation invariant measure on real line, and that is the length function. So, this gives us the fact that lambda, the length function on BR, the Borel sigma algebra of subsets of real line, is the unique translation invariant measure such that the length of the interval 0, 1, here comma is missing. So, 0, 1 is equal to 1, and this is a very important property of the length function. So, if you observe on the real line, there is a notion of addition, and we just now pointed out that the group operation x comma y goes to x plus y is a continuous map. And one can also easily check that x going to minus x, that is the inverse in the group operation, is also a continuous map. That is summarized by saying that the real line is a topological group. So, on the real line there is a topological structure, there is a metric, there is a topology on the real line, there is a group structure on the real line, and the two behave very well with respect to each other, saying that the group operations x comma y goes to x plus y and x goes to x inverse, both are continuous maps. So, one says such a thing is called a topological group. So, the real line with addition and the usual metric, the normal metric forms what is called a topological group, and we have shown on this topological group there exists a translation invariant measure. On the sigma algebra of subsets of it, there exists a translation invariant measure. This is a very important fact, and that can be generalized to what are called locally compact topological groups, that on every locally compact topological group there exists a invariant measure. Because the group may not be abelian, so one has to make a specific thing. There exists a left invariant or a right invariant measure on every locally compact abelian group, and that plays an important role in doing analysis on such groups. So, just a pointer that you may come across in your other courses in higher studies of higher mathematics, that on every locally compact topological group there exists a invariant measure, and that actually is called Haar measure on the topological group. So, Lebesgue measure on the real line is an example of Haar measure on the locally compact topological group real line under addition and the usual multiplication, usual metric space topology. So, these were the properties of Lebesgue measurable sets vis-a-vis group structure. Now, let us look at properties of the Lebesgue measurable sets with respect to topologically nice subsets of the real line. Namely, topologically nice sets are open sets and closed sets. So, we will prove, we will actually analyze and characterize measurability of sets in terms of open sets and closed sets. So, this is the precise theorem that we are going to prove. Namely, if E is any subset of the real line, then the following statements are equivalent, saying that a set E is Lebesgue measurable is equivalent to saying that for every epsilon bigger than 0, there exists an open set G lower epsilon such that E is a subset of G epsilon. That means, that open set includes E, and the difference between the two sets has got outer measure small. So, that means, there is a little difference between a Lebesgue measurable set and open set which covers it. So, we will show that for every a set E is Lebesgue measurable if and only if for every epsilon bigger than 0 there exists an open cover of it such that the difference between the cover and the set. So, lambda star of G epsilon minus E is small, and we will show that this is equivalent to saying that there exists a G delta set G such that the set includes E and the difference has got measure 0. A set G delta set, what is a G delta set? A G delta set is nothing but an intersection of open countable intersection of open sets. So, subsets of the real line or in any metric space which are countable intersections of open sets are called G delta sets. So, let us prove this theorem. So, saying that these three statements are equivalent is saying that if one of them holds, then the other one also holds. So, what we are going to do is we will assume 1 and show that 1 implies 2, and then we will show that statement 2, if you assume statement 2, that implies statement 3, and if you assume statement 3, then that implies 1, and that will imply that all these statements are equivalent. So, if one of them is true, then the other two statements are also true. So, that gives you a characterization of Lebesgue measurable sets in terms of open sets or G delta sets. So, let us prove this theorem. So, we will start with looking at. So, let us assume. So, let suppose the statement 1 holds. So, that is E is Lebesgue measurable. To show 2, and that is for every epsilon bigger than 0, there exists a set G epsilon open such that G epsilon includes the set E and the Lebesgue outer measure of G epsilon minus the set E is less than epsilon. So, this is what we have to show. So, let us start with something, this is regarding outer measure. So, let us start looking at the set E. So, let us first suppose E is such that E is Lebesgue measurable. So, let us suppose that Lebesgue measure of E is finite. So, what is Lebesgue measure of E? Recall, Lebesgue measure of E is same as its outer Lebesgue measure, which is same as infimum over sigma lambda of I j 1 to infinity, where the set E is covered by union of I j's intervals and each I j open. So, recall we had made a observation that in the definition of Lebesgue outer measure, you can assume that all the intervals involved are open. So, now, let us fix B fix, and since this number is finite and it is an infimum. So, by the definition of infimum, there exists a covering. So, there exists intervals I j's such that E is contained in union of I j's, each I j open, and we have got the property, namely lambda star of E, which is same as, so lambda star of E, which is same as lambda of E because it is measurable, plus the small number epsilon is bigger than sigma lambda of I j, j equal to 1 to infinity, right. So, and that implies, so this implies, so note lambda star of E is finite. So, this is finite quantity. So, that implies sigma lambda of I j, j equal to 1 to infinity is finite. So, all the sets have got. So, this implies that if I take a look at lambda star of union I j, j equal to 1 to infinity, that will be less than or equal to summation j equal to 1 to infinity lambda of I j by the subadditive property of the length function, and that is finite. So, this set union of I j's is a set of finite outer measures. So, let us define. So, put G epsilon to be the set which is union of I j's. And now, let us note that first of all G epsilon is open. Why it is an open set? Because each I j is an open interval. So, a countable union of open intervals is an open set, is open, and E is inside union of I j's. So, E is contained in G epsilon, right. So, we have got the required property that we have got a cover of E by an open set, and let us note and what is the difference. So, lambda star of G epsilon minus E. Now, note G epsilon is an open set. So, it is a Borel set. So, it is a Lebesgue measurable set, and E is given to be Lebesgue measurable, and it is a subset of it, and everything is finite that we have just now observed. So, we can say this is equal to lambda star of G epsilon minus lambda star of E. So, here we are using the finite additivity property of the length function, and lambda star of G epsilon, that is here, is that is same as lambda star of union I j, because G epsilon is union I j minus lambda star of E, and that is less than or equal to sigma by subadditive countable subadditive property 1 to infinity lambda star of I j minus lambda star of E, and that by our choice of our intervals I j's. If you recall, this was the choice. So, that means lambda star of this summation minus this is less than epsilon. So, which is less than epsilon. So, lambda star of G minus G epsilon minus E is less than epsilon. So, that means what? That means we have proved the required property when lambda star of E is a finite set. So, thus, if lambda star of E is finite, then 1 implies 2. Okay. Let us remove this condition, and that condition here is a step, here is an important step which should keep in observation, that we first proved a property about the length function for finite sets of finite measure, and now we are going to extend this using the fact that lambda is sigma finite. So, whenever you want to one wants to prove a property about the length function or about sigma finite measures, many a times it is easier to prove it when the underlying set is of finite measure, and then extend it to sets general sets of sigma finite measure.